everyone, and welcome back to another chapter of our physics O-level lessons. Today is our 9th chapter, and it is called Magnetism. In this chapter, we're going to be learning about magnetic poles, magnetic induction, how we make a magnet, magnetic and non-magnetic materials, where magnetism comes from, the magnetic field, and the Earth's magnetic field. As you can see, it's a very small chapter. And after this chapter, we're going to learn the electromagnets. That is going to be the 10th chapter. So let's see what magnetism is. So magnetism is a physical phenomenon produced by the motion of electric charge, which results in attractive and repulsive forces between objects. It may sound like static electricity when we learned about charges, because in that we also have attractive and repulsive charges. But this is different. But this is related to magnetism, not electricity. So the magnetic force of magnets seems to come from 2 points called the poles of the magnet. Here you can see this magnet. It has a north pole and a south pole. So the Earth exerts forces on the poles of a magnet. If the magnet is in air, it swings round until it lies roughly north to south. This effect is used to name the 2 poles of a magnet. The north-seeking pole, which is also called the N pole, and the south-seeking pole, the S pole. Here you can see them. S stands for south-seeking pole and N stands for north-seeking pole. So, if you bring the ends of 2 similar bar magnets here, like this has south pole here and north pole here, and this one has a north pole here and south pole here. So when we bring both of these together, the north poles of them together, there is a force between them. This is the repulsion force. Whereas when we bring a south pole close to the north pole, there is attraction. So this tells us that like poles repel and unlike poles attract. So it's almost like static electricity and the charges we read before in the previous chapter. But remember, do not confuse them, because magnetism is itself a different phenomenon. Both are different things, even though they may sound very similar. So the closer the poles will be, the greater would be the force between them. So like poles, whether they are north and north or south, when they are brought close to each other, north with north, there will be a repulsion force. These are like poles, so they will repel from each other. But if we bring unlike poles together, like south and north, they would attract with each other. So now that we've understood magnetism and the magnetic poles, we can move ahead onto understanding magnetic induction. So, materials such as iron and steel are attracted to magnets because they themselves become magnetized when there is a magnet nearby. So the magnet induces magnetism in them. Like we read, induced charges in the previous chapter. When we used to bring any object close to an electric field, it also used to get induced. The charges used to get induced. So if we bring a negative charged object close to a wall, the wall would get a positive charge, so that is an induced charge. In the same way, in magnetism, when we bring a material such as iron or steel in a magnetic field, they would also become magnetized. So the magnet induces magnetism in them. It's pretty easy to understand, right? Because we've read it before, something like this. Except for that was electricity. So the magnet induces magnetism in objects like iron or steel. So here we have an experiment which shows this. So here we have iron and steel, and there is a magnet here. The iron and steel are undefined right now, so there are no poles shown. When they are put here, afterwards they get attracted to this magnet, and you can see, because the magnet has a north pole, in each case the induced pole nearest the magnet is the opposite of the pole at the end of the magnet. So the attraction between unlike poles holds each piece of metal to the magnet. But the steel and iron behave differently when they are pulled right away from the magnet. As you can see, iron loses its magnetism and goes back to its normal physical state. But steel becomes permanently magnetized. So you can see that iron was only a temporary magnet, but steel becomes a permanent magnet. It has the South Pole and North Pole even after it is pulled away from this magnet. So this depends on the material. What material is a temporary magnet and which one is a permanent magnet? Steel is a permanent magnet, so when it is placed in a magnetic field, it becomes magnetized and it is permanent, so it is hard to get that magnetism away from the steel. Whereas iron was not very magnetic, so when it was placed in a magnetic field, it was only a temporary magnet. When we took it out, it went back to its normal state. So this is the difference between steel and iron, and it depends on many different other materials. Some materials would be good magnets and some would be not very good magnets. So now we're going to look at how we make a magnet. A piece of steel becomes permanently magnetized when placed near a magnet. This is one way we can make a magnet. The piece of steel becomes a magnet when it is placed near a magnet, but it can be magnetized more strongly by stroking it with one end of a magnet. Like if we bring a magnet close to the steel bar and stroke it, go from one pole to the other and then go back to the first pole and then the second one. Something like this, we make the circular movement and the steel would be more strongly magnetized. However, the most effective method is to place it in a long coil of wire and pass a large direct current in the coil. The current has a magnetic effect which magnetizes the steel. So, we have a coil of wire in which we place the steel bar. We pass a large direct current in the coil. So the current induces magnetism in the steel and the steel becomes magnetized more strongly than either of these methods would. These are the three ways we can make a magnet. The first method is to place the steel bar near a magnet. The second method is by stroking it with one end of a magnet. Only one end, we don't have to put another end. The last method, which is the most effective method, is to place it in a long coil of wire and pass a large direct current in the coil. So the current has a magnetic effect which magnetizes the steel. So this is how we make magnets. Now, as I said, steel and iron, they are two different materials. Iron was a temporary magnet and steel was a permanent magnet. So speaking of different materials and magnetism, we're going to look at magnetic and non-magnetic materials. So a magnetic material is one which can be magnetized and attracted to magnets. So all strongly magnetic materials contain iron, nickel or cobalt. For example, steel is mainly iron, that is why it was a good magnet. It became permanently magnetized. Strongly magnetic materials like this are called ferromagnetics. So the materials which are good magnets are called ferrous materials, whereas the materials which are not good magnets are called non-ferrous. So iron and alloys containing iron are called ferrous materials. Ferrum is basically a Latin word for iron. Aluminium, copper and the other non-magnetic materials are non-ferrous. So ferromagnetics are described as hard or soft, depending on how well they keep their magnetism when magnetized. So first we're going to look at the hard magnetic materials. Hard magnetic materials such as steel are difficult to magnetize but do not readily lose their magnetism. So they are used for permanent magnets. Like steel. Steel, it might be difficult to magnetize it because it is a hard magnetic material. But when it is magnetized, it does not readily lose its magnetism. Like once it is pulled away, it won't go back to its normal state. It will stay permanently magnetized. So hard magnetic materials are used for permanent magnets. Soft magnetic materials such as iron and mu metal are relatively easy to magnetize, but their magnetism is only temporary. And so they are used in the cores of electromagnets and transformers because their magnetic effect can be switched on or off or reversed. So even soft magnetic materials have their uses. Soft magnetic materials are the ones which can be easily magnetized but their magnetism is only temporary, like iron we saw in that experiment. When it was placed near the magnet, it was magnetized and it was easily magnetized, but when it was pulled away, it came back to its normal state. So that shows that it was only a temporary magnet. Now, such magnetic materials, the soft ones, they are used in the core of electromagnets and transformers. So electromagnets have their magnetism effect with electricity. Like we may see machines, the magnetic machines which can be turned off and on. When we turn them on, there is a magnetic effect in those, and so they pick up the objects, the ones which are attracted to magnets, like iron and steel. They stick to this electromagnet, and then we can move these objects all together with this magnet, take it to another different place. So when we turn the magnet off, the things will fall down. You might have seen such machines. This machine has an electromagnet in it, and this electromagnet can be switched on or off. Now, for electromagnets, we need a material which can be easily magnetized, and then it can lose its magnetism as well easily, so that we can turn it on or off whenever we want to, like in that machine. So here is where the soft magnetic materials come in, because they are easy to magnetize, but their magnetism is only temporary. So I hope you've understood hard magnetic materials and soft magnetic materials. Lastly, we have the non-magnetic materials. These include metals such as brass, copper, zinc, tin, and aluminium, as well as non-metals. So they do not get attracted to magnets. They are non-magnetic materials. Neither they are temporary magnets nor they are hard magnets. They just don't get induced. So these were the materials, hard materials and soft magnetic materials. I hope you've understood them and the uses of these materials. So now we're going to move ahead onto understanding where magnetism comes from. So this is a question which might come in our heads at one point. Where does this magnetism come from? So where does magnetism come from? Here we have the answer to this question. In an atom, tiny electrical particles called electrons move around a central nucleus. Each electron has a magnetic effect as it spins and orbits the nucleus. So, in an unmagnetized material, the atomic magnets point in random directions. But as the material becomes magnetized, more and more of its atomic magnets line up with each other. Together, billions of tiny atomic magnets act as one big magnet. So if a magnet is hammered, its atomic magnets are thrown out of line, so it becomes demagnetized. Heating it to a high temperature has the same effect, because the atoms and the material deforms and its atoms go out of line. So this is where magnetism comes from basically, in tiny atoms. So there are tiny electrical particles called electrons which move around a central nucleus in an atom. So each of these electrons has its own magnetic effect as it spins and orbits the nucleus. Why is that? Nobody knows. But yes, this is how it is. This is where magnetism comes from. So together, billions of these atoms together, they make up a magnetic field. So if the material becomes magnetized, more and more of its atomic magnets line up with each other. Billions of tiny atomic magnets act as one big magnet. So, speaking of magnetic fields can be investigated using a small compass. Now, the needle in the center of this compass is a tiny magnet which is free to turn on its spindle. So, when this is near a magnet, the needle is turned by the forces between its poles and the poles of the magnet. So, the needle comes to rest so that the turning effect is zero. So here you can see the diagrams. So there is a magnetic field around every single magnet, and this exerts forces on magnetic materials in it, where if there are any magnetic materials in this field, a force would be exerted on them. Here we can see how a small compass can be used to plot the field around a bar magnet. Starting with the compass near one end of the magnet, the needle position is marked using 2 dots. Then the compass is moved so that the needle lines up with the previous dot, and so on. So when the dots are joined up, the result is a magnetic field line. More lines can be drawn by starting with the compass in different positions. So you can see, if we place so many compasses around a bar magnet, they would line up to show such kind of pattern. This is the magnetic field. It is strongest at the ends of the poles, with the nearest of the poles, and becomes less as it moves away from it. So this is how a compass can be used to draw such lines. So in this diagram, a selection of field lines has been used to show the magnetic field around a bar magnet. The field lines, as you can see, first of all, the field lines run from the north pole to the south pole of the magnet. The direction in which the force on a north pole would act is the direction in which the north end of a compass needle would point. So, if the compass needle's north pole acts in any direction, it is directing towards the north pole. And secondly, the magnetic field is strongest where the field lines are closest together, which are the ends of the magnet. So, if 2 magnets are placed near each other, their magnetic fields combine to produce a single field. So for example, if we have a north pole with the north pole, the magnetic field would be different, but it would be a single field. They would repel from each other. And the neutral point is the center of the field. At the neutral point, the field from one magnet exactly cancels the field from the other. So the magnetic force on anything at this point is 0. If the magnets are unlike magnets, the field would combine together. So the fields from the north pole of one magnet would go towards the south pole of the other magnet. Now, another way of plotting a magnetic field is by using iron filings on a paper over a magnet, as you can see in this picture. So these are iron filings, they're like small iron bits. So we have put a bar magnet here and we throw some iron filings over it, and they start to move and they start making this pattern. Now once we remove this bar magnet, I don't think we would be able to do that because the iron filings would simply stick to it. But if we just keep it there, you can see there's this pattern of these iron filings which make up the magnetic field around a magnet. And you can see that the iron filings are closest at the ends of the magnet. So they are closest over at this point, because this is where the magnetic field is strongest. The ends and the middle part, the magnetic field is not stronger at this point. So the magnetic field gets weaker and weaker as we move away from the magnet, and it is strongest closest to the magnet. Now, some electronic equipment is easily upset by magnetic fields from nearby generators, motors, transformers, or even the earth. So let me tell you, the earth also has a magnetic field. We're going to read it right now, just in a minute, but let me just finish what I was talking about. So the equipment can be screened, which means that it can be shielded by enclosing it in a layer of a soft magnetic material, such as iron or nickel. Now this magnetic material, although it is magnetic, so it will also become magnetized, but what it will do is that it will redirect the field so that it does not pass through the equipment. So this is what magnetic screening is. Okay, now that we've understood what a magnetic field looks like and how we can find a magnetic field by using a compass and where magnetism comes from, we are going to move ahead onto understanding, and this is going to be the last topic of this chapter, the Earth's magnetic field. Now here we have the Earth's magnetic field. You can see that the Earth also acts as if it's a big magnet or something. And these are the poles of the Earth. Now, the Earth has a magnetic field. The north end of a compass needle points north, so it follows that the Earth's magnetic south pole must be in north. Because of course, the north pole of a magnet would point at the south pole of the other magnet. So this means that the Earth's magnetic south pole must be in north, but we call it as the north pole. So, for example, in this image, this is the South Pole. Then this must be the magnetic North Pole of the Earth, because if a compass needle's South Pole pointed this direction, then obviously there should be a magnetic North Pole at this point. But we call it the South Pole, the geographical South Pole. And this is going to be the geographical North Pole. So, this is the Earth's magnetic field. The Earth behaves as if it has a large but very weak bar magnet inside it. So this is the Earth's magnetic field. I hope you have understood. Now this was it for today's chapter. As you can see, this is probably the smallest chapter we've ever read and understood, right? Yes, it was a small chapter, but the next chapter, which is going to be electromagnets, and that chapter is related to magnetism because it involves magnets as well. But in that chapter, we get involved into magnetism and current. So that's going to be electromagnetism. That's going to be our 10th chapter. But for now, this was it for magnetism. We read all the chapters here and I hope you've understood them. And this was a pretty simple chapter. It was just stuff to learn and information. But yes, you have to remember all this because it's going to help anyways in the next chapter. So there were not any equation in it, just stuff to understand about magnets. Magnets, magnetic poles, magnetic induction, how we make a magnet, magnetic and non-magnetic material, and so on. The Earth's magnetic field as well. So I hope you've understood this chapter nicely. Thanks for watching this video. Make sure you remember everything, and I'll see you in the next chapter.